Hello there, and welcome to Forces Part 2. We are in a new booklet now, just lessons 5 and 6 in this booklet. And lesson 5 is going to be on forces and elasticity. So this one, there is a required practical in here. Depending on what the current situation is like, you may be able to do the practical, but there is a video that you can watch on YouTube from Malmesbury Science that you can watch the actual practical being done. And in that one, you can get the data from it and also see what you were supposed to do. And then from there, we're going to be focused in this lesson and the next one. We're going to be focusing on a certain equation called Hooke's law, where we figure out spring constants and the such. So the do now in the beginning of the lesson, can you please finish that and pause the video? We'll go over it in a second here. Right, so here are the answers. Please make sure that you are correcting them as you go along. But most of this should be pretty straightforward, quite easy. All right, so today we are looking at Hooke's law, and you're going to hear that name quite a bit in this lesson and in the next because we're talking about elasticity and we're talking about extensions and compression of springs. But today we're going to be looking at the introduction for that. So we're going to see the extension of elastic objects and also the equation that links the force and the extension of a spring. So when we talk about elasticity, we're talking more or less about how well an object can deform when some force is applied and return to its original shape when that force is then removed. So just think of any spring. You might be thinking of like your bed springs, something like that. And when you pull on it or push on it, you're applying a certain force. But once you remove that force, so maybe if we're talking about bed springs, once you get off the bed, then if your bed springs have really good elasticity, then it'll return to that shape again, the original shape. All right. And this is kind of a new thing because so far we've been looking at when we're just pushing or pulling an object. So we're really working in a unidirectional way where you push and you pull. The thing about elasticity is we're now thinking about, well, what happens to an object when you have more than two forces, okay, or two or more forces. So looking at line 8 here, we're going to say if the object is pushed from both sides simultaneously, it may change its shape. It is compressed. If the object, all right, so we know that, let's highlight that there because we're looking at now two forces, and now we're focusing on what happens to the object when those two forces are applied. If the object is pulled from both sides simultaneously, it may become stretched. So that's the diagram on the left there with the arrows, red arrows. Okay, so when you have two forces going the opposite way, you have extension. If you have two forces going inwards towards the object, then you have compression. The other two, where you have the metal bar and the green arrows, and the person with the two supports on his hands and the load going downwards, that we call bending. All right, so objects can also be bent by applying forces to different points on an object. So depending on what object you have, you're going to have a bending force on that as well. All right. When we talk about an object changing shape due to a certain number of forces being applied to it, we call that deformation. All right. So, for instance, all those shapes that you see in the diagram, so the spring, the metal bar, and what looks like a ruler on the right diagram, they're all going under deformation. And we're going to talk about, well, is there a difference between if it stays that shape after it's deformed or when it springs back? We have different names for those. So on the next page, you'll see there's a table that asks for examples of stretching, compressing, and bending, as well as diagrams of the forces applied. So this should be pretty straightforward. You have some of the diagrams on the previous page. In the examples, we're not really going to put in lifestyle examples, but because you probably already know these. But what we're going to do is we're going to kind of explain in words what's happening in the diagrams that we draw on the right side of this chart. So go ahead and pause the video. I would recommend starting with the diagrams first with the forces and then kind of describing those forces in the example column. All right, so pause the video really quick and do that. Right, so hopefully by now you have all 6 boxes filled in. I'm going to go in order here with each one. So I'm going to start off with stretching. So stretching is when you have two forces of tension acting away from each other, okay? Or you could have also said that the two forces are acting away from the object in focus here. And your diagram should look something like this, where you have an object in the middle and two forces going out. For compressing, it's going to be exact opposite. You have two forces acting toward each other, or same thing. You could say two forces that are acting in towards the object, right, from opposite sides. And your diagram will look something like this, right? So an object in the middle, two forces going into that object. The bending one is probably going to be the most confusing to describe because this one you're going to need a minimum of three forces, and it's a combination of both stretching and compressing. The diagram I'm pulling from the exact one from previous, and you have the two forces on the left are obviously compressing, but if you compare the arrow going up and the arrow going down on the right side, those are going to be stretching because they're technically going in opposite directions, but they are both going inwards but at different angles. So this one is actually quite difficult to explain, but if you can kind of burn that image into your mind right now about what bending looks like, that'll help you in the future. All right, so now let's talk about this deformation stuff. Some of the above examples may include objects which return to their original shape once those forces are removed. All right, so think of a spring again. An object is said to go elastic deformation when it returns to its original shape after the forces are removed. So that's your first definition right there. All right, and if you want to underline elastic deformation, then go ahead and do that. But we say that it's elastic because it returns to its original shape, right? So you can talk about or think about like a rubber band, an elastic rubber band, right? After you stretch it, it should kind of go back to its original form once you've let go of that rubber band. The opposite of that is called inelastic deformation. And in inelastic deformation, this is when you stretch an object and it stays in that stretched position even after you've let go of it, or in other words, you've kind of removed those forces. Okay, so the example that they give you here is modeling clay. And if you've ever played with modeling clay, or I think the more common example is Play-Doh, you can stretch that clay, right, and kind of shape it into whatever you want. But once you've let go of it, it will actually stay in that shape. All right, so that would be inelastic deformation, where you apply a force that kind of changes the shape of the object you're working with, and even after you've removed all the forces to it, it will stay in that shape. So that's kind of your checkpoint question. Hopefully you understand what that means. What is meant by inelastic deformation? So the way that I've worded this is a material will not return to its original shape when the deforming forces are removed. Okay. Now we get to the part where we're going to investigate how force and extension are closely related. And this is a required practical, and like I said in the beginning of the video, depending on the circumstances, you may be able to do this in class, or you might have to just watch the video and see what's happening. But in a nutshell, we're going to read the summary here. What we're doing is we're hanging a mass on a spring, and we're going to increase the mass and see how far that spring stretches. All right. So hang different masses from a spring and measure the extension of the spring for each mass used. Convert the mass into weight. Use the results to plot a graph for extension against weight. So by now you should know that you can convert your mass into weight by using the formula weight equals mass times gravitational field strength. And your gravitational field strength is going to be 10 newtons per kilogram, or you can use 9.8 newtons per kilogram. Either or works. Should be fairly close. All right. And this way, when you're adding on a mass of, say, 500 grams, 1 kilogram, 1.5 kilogram, 2 kilograms, you can change that into a force to then use in the equation that we're going to use later on. And from there, once we get all the data, we should be able to plot a graph that has extension on one axis and the weight on the other. Okay. So this is the diagram of what your practical would look like. You have a clamp to hold the ruler as well as the spring, okay? And obviously there's a lot of safety issues here. You want to make sure that everything is um, clamped onto the table, nothing's moving around, because when we're working with springs, as you know, even with like rubber bands, if they're somehow loose in a sudden motion, it can kind of snap and fly somewhere, and you don't want that getting into any sensitive places on your face. So when you're doing this practical, you have to make sure that every safety precaution is met. But other than that, it's a pretty straightforward practical here, where you have the spring and you keep adding on more and more weights. You wait for it to stop going up and down, and you look on the ruler and see how far that it's extended. Okay. Before you go and watch the video, I do want to talk about some variables, because this is a really popular question that GCSEs ask. They might give you a practical that you've done before or that you should know, and they'll ask you, what are the variables? What's the independent variable? What's the dependent variable? So if you want to take a minute or two, pause the video and think about what's your independent variable and what's your dependent variable. Go ahead and do that. Right. If you got to the same conclusion as I did, great. The independent variable that I wrote down was that the amount of weight attached to the spring. So remember that the independent variable is the one that you can control. Okay? Well, the one that you're changing, and you're hoping that there will be a response to the change that you already did. All right? So the reason why the amount of weight is your independent variable is because depending on the weight that you attach, it should change the amount of extension there is. Also, I added on there, just kind of as an additional thing, the type of spring used. So hopefully you know that the spring in your bed is a little bit different from the spring that you might find, let's say, on a trampoline. Okay, and so all these springs have different strengths, and depending on the spring that we use in this practical, you might get a different spring constant, and you'll understand what I mean in a little bit here. The dependent variable is going to be the extension of the spring. So this is what we're measuring, right? The dependent variable is what we want to record in our data, because that's what's going to be changing due to the independent variable. Okay? So this is the video that you are required to watch if you don't have access to the practical. It's basically the same thing that we would have done in class, and it's titled Hooke's Law, and you can look it up on YouTube, Malmesbury Science, and just type in Hooke's Law, or if you go to the tiny URL link at the bottom here and just type that into your browser, that will work as well. Okay, up to you. And once you finish watching the video, then you can come back to this one, and then we'll carry on with what the practical, or sorry, with what the rest of the booklet has us to do. All right, so hopefully you've watched the video. The data that I have here is straight from the video that you just watched, okay? Because I want to use the same data that you have in your booklets, hopefully, okay, if you weren't able to do the practical. So on the left column, you have your weight in newtons, and that's going to be from 0 to 5, all right? The 0, don't need to write in anything there because it's given to you, but the 0 is there as a control. As with most experiments, you need to have a control to make sure that you know that your experiment is going to be credible. All right. So this data is basically telling us that when we put on 1 Newton of weight, there was an extension of 3.5 centimeters. When there was 2 newtons of weight, there was 8 centimeters of extension, and so on and so forth. The middle column here is what I would have had you done if you did this in class. And the way that you find this is by basically measuring the entire length of the spring. So as you add on more weights, you're going to find that your spring is getting longer and longer. Okay. So what you're going to do is you're going to get that measurement, okay, and you're going to subtract it from the original length of the spring with no weights added onto it. All right, and that's how you get your extension. That should more or less make sense. It is kind of an extra step, because what you're doing is you're trying to be as specific as possible, or as accurate as possible, instead of just kind of guessing, well, where was the start point of the spring and how much are we measuring here? All right, so you have basically you're looking at the left column and the right column, and that's your x and y axis. Because what we're going to do now is we're going to plot these points. So on that page, you'll find that there is a part there where it's given you a graph as well as an x-axis and a y-axis for extension and for force. So one of the skills that hopefully you have by now is you know how to plot a graph. This should be more or less one of the easier things that you need to do, where you just choose a scale on your x-axis and choose a scale on your y-axis. That's probably going to be the most difficult part because some students have difficulty choosing, well, how, like, does each box equal 1 or can I change that? And the answer is yes, you can make your scale to whatever scale you want, it just has to be accurate. So I've gone ahead and I've put this into Microsoft Excel that gave me a chart that looks like this, sorry, a graph that looks like this. So you'll notice that at 0, it's at 0 extension in centimeters. At 1 newtons, it was at 3.5, I believe, and so on and so forth. So with your graph, you can be a lot more accurate with this because you have more lines. But your x-axis, which has your force in newtons, should be pretty simple. It should just go 0, 1, 2, 3, 4, 5. Your y-axis for extension might be a little bit more specific because it is going into decimal points. So try and be as specific, or sorry, as accurate as you can on your y-axis. But from here, what you're going to do now is draw a line of best fit. And a line of best fit, as you hopefully remember, is basically a straight line, okay, not a curved one. You don't want to connect these lines, but it's a straight line that goes through as many points as possible. All right, and a good way to figure out if you've got a good line of best fit is you should have an equal number of points on both sides of the line. So in this one, you'll notice that I have 2 points on top of the line and 2 points below the line. And the one at 3 newtons is kind of right on the line, so that one doesn't matter that much, okay? So there is your chart from the data that we just got from the video. And if you did this in a classroom, your line of best fit might be a little bit harder to grasp depending on how accurate your data was. Okay. Right, so let's analyze some of the data that we got. Looking at your chart with the line of best fit, okay, you should be able to tell me what the trend is. So number 1 asks, what happens to the spring as the weight is increased? And that should be pretty simple. Your spring is being extended as you add in more weight. Number 2 asks, did you draw a line of best fit? Quite simple, yes we did. Number 3 is asking, describe the shape of the graph. So this one, I'm going to use the mathematical term here, which is linear. All right, it's not a curve, it's just a straight line. Okay, that's the shape of the graph that we want to talk about. And from there, we need to understand what's the relationship between force and extension from the graph. Well, we can say that it's a linear relationship, which means that as one increases, so does the other. So in this case, as force increases, as we go from 0 to 1 to 2 to 3, then your extension increases as well. And this is actually what's called a proportional relationship as well, or we can say that force is proportional to extension because we can conclude from the graph that as one increases, so does the other. All right. Number 5 asks, describe the form of energy stored in the stretched spring. So this one, if you have a spring that's stretched out, what type of energy is in there? It is elastic energy. I will also accept elastic potential energy because it is a type of energy that's not kinetic. Okay, but from elastic energy, that should be kind of pretty straightforward that it is potential energy. And number 6 asks, describe the type of deformation undergone by the spring. And this one should be, hopefully, elastic because it returns to its original shape after the weights are removed. If you find that after you remove the weights, the spring does not go back to its original shape, then what you have is inelastic deformation. All right. Okay, so there's going to be quite a few annotations on this page, so make sure you are writing to give yourself enough space, all right? So there's my fair warning there. The results of the above investigation reveal a straight line graph which shows the extension is directly proportional to force. That should make sense because one is increasing as the other. if we continue to increase the force, in other words, if we continue to keep adding on weight beyond something, eventually we would find a situation where the spring remains permanently deformed. Okay? Kind of like if you have a rubber band, if you keep pulling and pulling and pulling and pulling, at some point that rubber band is going to snap, and what you have is just a long string of elastic rubber. Okay, so if you want to highlight that sentence there, okay, because that's actually a pretty important observation, and there's a name for this. There's a name for when you stretch something so far that it becomes permanently deformed, and we call that elastic distortion. And elastic distortion is known for the extension and force exerted to what's called the limit of proportionality. All right, and that's labeled right on the graph there. And you'll notice that the limit of proportionality is where the graph doesn't become linear anymore, it actually becomes a curve. Okay? And the limit of proportionality is the point at which the material will not return to its original shape even if the force is removed. Okay? So that's kind of, you can almost call it like your breaking point. All right? So if you're thinking about a spring, there will be a time where you stretch the spring and it won't return back because you've basically stretched it too far, and whatever that material that the spring is made out of, usually metal, it just kind of stays in that shape. All right? So limit of proportionality, kind of almost like the breaking point, and every spring has one. All right? Okay, so let's look at the graph a little bit more. And I'm going to focus more on the linear part of it because that's what you have in your booklets right now. When you actually calculate, and you might have noticed this if you watched the video from Malmesbury Science, what he did in the video is he calculated the slope of the linear graph. And the gradient, or the slope, of that line represents what's called the spring's constant. And I'm going to explain a little bit more what the spring constant is. But the spring constant is basically how strong a spring is. And the bigger your spring constant, the more force that you're going to need in order to stretch it out. Okay? So in a graph, what it will look like is if you have a really big spring constant, then you have a really big gradient. And that's going to look like a very, very steep slope. Likewise, if you have a low spring constant, so it's not a very strong spring, then the slope will be very shallow. Okay? So that's what this graph is going to represent. When you have a force against extension, that's where you get that. Now, another thing that's important to realize here is energy, right? Because what we said previous was the energy stored in a stretched spring is elastic energy, or elastic potential energy. And you can actually find out how much energy is in this spring. And the way to do that is by looking at all the energy that's stored under the graph. So if you look at the graph right now, the purple shape that's on there right now is somewhere around 5.5 newtons. So when there's 5.5 newtons pulling on this spring, I can calculate the area underneath the graph, and that will tell me how much energy is stored inside the spring. And I can do this for as much as I want. I can even go down to how much energy is stored when there's 2 newtons of force in the spring. So then I would kind of highlight the area underneath the graph up to 2 newtons. Okay, so there'd be a line going straight up from the x-axis at 2 newtons up to the graph, and I would highlight in that area. And when I calculate the area of that space, that's how much energy is in the spring currently. Okay, but it's more of a concept question where if you understand that how much energy is stored under the spring, then you can figure it out by looking at a graph and looking at the area underneath the linear line that you have. All right, so now we get to some of the equation stuff, and we're going to look more into this next lesson. But from that graph that you just saw, from 5.5 newtons onwards, the extension is no longer proportional to force, which means that it kind of goes, that's your breaking point, it kind of goes off the scales. And actually, this is where Hooke's law doesn't actually apply anymore. All right? So the point is called the limit of proportionality, but up until the force, or up until the limit, force is proportional to the extension for straight line section of the graph. So remember this symbol between the F and the E, right? F stands for force, E stands for extension. That's the symbol for proportionality. Kind of looks like a fish, all right? And so what that means is if we doubled the force, then your extension would be doubled as well. That's the perks of having a linear graph. It's quite easy to kind of see, well, if we double this, then that else should be doubled as well. And so we're going to talk about what happens before that limit of proportionality. To change this to an equivalence relationship, a constant can be added to the equation, and we call that the spring constant. And the denotion, or we denote the spring constant by the letter k, a lowercase k. All right. So here's your new formula. Unfortunately, again, you're not going to get this on your GCSE, so you do have to remember it, unfortunately. It is an easy one. It's just F equals K times E. And there is a name for this equation, and that's called Hooke's law. All right, kind of the same as Ohm's law when we're talking about electricity. It's just a simple equation. All right, so this is Hooke's law. And again, please, please, please remember the units for these. Nothing really that much new because force, as you know, is measured in newtons. Extension is a measure of distance, and with science, there's always an SI unit, so we're going to measure distance in meters. For the spring constant, it is measured in newtons per meter, all right, and that's just because we're talking about springs here, so depending on how far it's stretched, then there's a different amount of force that's applied as well, okay? And you can just add on there, as I said previously, the higher the spring constant, the stiffer the spring, okay? And you can, if you rearrange the equation, you can get K equals force divided by extension, all right? And so if you have the amount of force that's applied and you have the measurement of how far it's stretched, you can find out the spring constant for that specific spring. And you'll notice that if you have a really high spring constant, it will require a much higher force to make it stretch. Okay, so every spring has a different spring constant, and you should realize or find out the relationship between the force and the extension of that spring. Okay, and like I said, we're going to look more into this in the next lesson. So if you don't understand right now, we are going to go way more in depth next lesson as well. Okay. And that's pretty much it for the entirety of this lesson. There is 9 questions for a knowledge check, so go ahead and pause the video really quick and answer these questions. I will reveal them in a couple seconds here when you're finished. Perfect, so here's number 1 to 9, and number 8 and 9 obviously are legacy questions from the electricity unit. So if you don't remember that, it might be a good idea to once in a while revise some of the circuit diagrams or circuit symbols, because there will be a question on circuits, and if there is, then you should know what these symbols represent and what they do at the same time. Okay? Other than that, thanks for watching another lesson, and I will see you in the next one.